as with any paper with 10 authors, I am the expert on some aspects and not the expert on others. So if you have questions, I will do my best to answer. Hopefully they will be questions in my wheelhouse. But here we go. So a Lie superalgebra, for everybody, is a Z2 graded vector space together with what's called a super bracket. So you take things that are both in the positive or both in the even, both in the odd, things like this. So it looks like the traditional Lie bracket, except you've got these conditions on where in this graded space you are. These conditions are given on homogeneous parts, but of course you can extend linearly. So there we go. So there are, in the classification of Lie superalgebras, there are three general types. There's basic, which looks like generalizations of your favorite classic simple Lie algebras. There's of Cartan type, and there's two families of so-called strange Lie algebras because they aren't basic and they're not of Cartan type. We're going to concentrate today on the paraplectic Lie superalgebra, and there's one more which is called the queer. So if you take a Z2 graded vector space and you consider endomorphisms over that vector space, this is your very basic favorite Lie superalgebra. It has in particular a Z2 grading where you look at the endomorphisms on the diagonal are the G0 part, and the endomorphisms on the off diagonal are the G1 part. What's the bracket? The bracket is your favorite Lie bracket, except it comes with, you pay for it on a grading. So that's GLMN, M being the dimension of V0, N being the dimension of V1. So if V1 is trivial, this is GLM. Back to your favorite space. Okay, so now if I put a bilinear form on this space, I'd say it's a supersymmetric bilinear form. Again, you pay for it on the grading. If you can study the invariant subspaces. So this is when you're defining Lie algebras, this is how you get things like the orthogonal Lie algebra or the symplectic Lie algebra, is that you say, okay, I have an even form or an odd form. Well, if I take an even form, what I get is the orthosymplectic Lie superalgebra, where on the even part, I get the orthogonal case, and on the odd part, I get the symplectic case. So it has both of those built in them. If I let beta be odd, that's when I get the paraplectic Lie superalgebra. So that's what this thing is I take all of the endomorphisms with my graded bracket, I put this supersymmetric form on it, and I look, if that supersymmetric form is odd, then I look at the invariance and I get the paraplectic Lie superalgebra. Not so hard. Of course, if it's an odd form, I need both of those V0 and V1 to be of the same size, or it reduces to 0. So what does this thing look like? Well, if it's an odd form, then anytime you pair an even with an even or an odd with an odd, I get 0. And even with odd or odd with even is a symmetric form. So beta looks like 0 on same degree stuff and symmetric on off degree stuff. Well, you can give an explicit description of this in terms of matrices if you pick your basis nicely. This looks like big square matrices where the upper corner square is negative the transpose of the lower corner square, and the off-diagonal square matrices satisfy some kind of transpose condition. So very physical kind of thing. As vector spaces, you can decompose it again into an even part or an odd part, but further you can decompose the odd part into a positive and a negative. So in particular, if you're trying to do representation theory, you like to study the Cartan and the Borel. We usually pick our Borel to be a Borel of this G0 part plus the lower diagonal stuff. So that's our favorite Borel for the case of this, but there are lots of good choices. Notice that this G0 part is isomorphic to GLN. Why? Well, because the top determinants the bottom, And the multiplication here is exactly just all n by n matrices. So that's GLN. So if you're looking for a Borel, you're taking a Borel of GLN, which is just, in this case, maybe lower diagonal matrices. It's a good choice. Okay, so our goal is to study the representations of this algebra, which on its face might not look so difficult, but it has been. I mean, the representations of all of the other Lee's superalgebras has basically been covered, and up until now, very little was known about the representations of the paraplectic Lie algebra. Certain representations were defined, and a little bit was known about them, but the general, what's the structure, what are the standard modules, what are the simple modules, how big are they, what are their, what are the simples inside the projectives, things like that, was not very well studied. So that's what we're embarking on and what that archive paper is all about. So in particular, we're going to study the category of finite dimensional integrable representations, just to give something to start with. All right, well, the problem with this category, the obstruction, has been that there is no duality functor that preserves simple objects. So there's sort of more than one choice about how you want to go about defining simple objects or standard modules. So projective modules do happen to be injective and tilting, but the standard and co-standard modules actually have different combinatorics. So this was defined as Katz was writing all about these superalgebras, defined a couple of different modules. We'll call them thick and thin Katz modules. So in particular, let's start with highest weight theory. Preserve standard, yeah. Okay, so if you're looking at the cartan is the cartan of GLN. So the weights are the same thing as GLN weights. Integer partitions with a shift. So decreasing integer sequences. Highest weight modules. Let V of lambda be the simple GLN modules. Let L of lambda be the simple P of n modules of highest weight lambda. Then we define the thick and thin Katz modules as inductions from the simple GLN modules. I think maybe this should read G0 here. So you induct up from GLN to the whole algebra, the thick and the thin. So induction and co-induction. And just looking at their sizes, the thick modules are predictably larger than the thin modules. So these are going to be our favorite standard and co-standard modules in this category. So Fn is a highest weight category with two natural highest weight structures. One is you can pick the thick Katz modules as your standard modules and the thin Katz modules as your co-standard. What's the ordering? It's kind of backwards from what you think it's going to be. You say mu is greater than lambda if the parts of mu are smaller than the parts of lambda. You can get it to flip if you choose different, you make different choices about the Borel and things like this, but here's our order. Or you could choose the standard modules being the thin modules and the co-standard modules being the thick. We go with the first choice. And we've been able to prove some nice things about these. So for example, there's a BGG reciprocity. The multiplicity of the thick Katz modules in any projective is equal to the multiplicity of the injective inside of, or the simple inside of an injective hull, and vice versa. When do you have thick modules appearing in projective covers? It's exactly by, yep, I think this is flipped. Anyhow, it's by highest weight things, by dominance order, and you have when they are equal, it's exactly when lambda has distinct parts. This is not us, this is us. In particular, one thing you might ask is, does this category have enough projectives? It does. In particular, nice induced modules are both projective and injective and tilting, so we've got lots of these kinds of things. Okay. So just as a disclaimer, to not muck up the waters too much, there is a parity switching involution on P of n, on its modules, things like that. Sometimes I'm kind of sweeping that under the rug. When do I mean the multiplicity of this inside that? It's of this or of its parity switched version, those kinds of things. But all the technical details are in the paper. Some of these, yes. Yeah. Exactly. So, let's talk about some of the combinatorics. The big part that was missing, many parts of this have been done, of what so far I've said have been done, some of the details we've finished up, but the big part is how do you move around in the category and how do you measure certain multiplicities? And the trick is that in other cases, you took some kind of large center of your enveloping algebra and used it to create endofunctors of certain translation functors and projections onto blocks to figure out what all of the interplay in the category is. The problem here is that the center of this Lie superalgebra is trivial. So even going and looking for your favorite central element, the Casimir, nope, not going to be in there. We've done something to get around that. That was the big spark, the moment that we figured out, okay, we can do this, and the genesis of this very long paper. Is that P of n sitting inside of GL and n actually does so very nicely. So with respect to an inner product, that's the super trace, except for on the odd part you subtract instead of adding. The dual of P of n is its orthogonal complement. So GL of n is equal to P of n plus its dual. The other piece is that GL of n is exactly GL of v. So this v0 plus v1 is a GL n module, it's a P of n module, and it's a Pn star module. So what we do is we build sort of a fake Casimir element, a split Casimir that lives not in P of n times P of n, but lives in P of n times P of n dual. It's the dual with respect to this form. I forget. I don't remember if it's, sorry? So odd isomorphism I might not, but what I do need is to be able to take a dual basis. Okay? But the dual basis to the basis in P of n to itself is not sitting in P of n. Okay? So I've built an operator that's out of the basis in P of n and its dual inside of GL of n. You don't necessarily need that it's in P of n star, fine, but I do need that I can find it somewhere. It's not in P of n. You don't need it. You don't need it. Yeah. Right. True, but you don't need it. I just need that it's there. Okay, so now this is my favorite Casimir element. It's not exactly a Casimir element. Casimir elements, split Casimir elements, usually you take some over a basis, B tensor B star, that lives in, G tensor G. Fine, this is not where this lives. But it does a lot of the things that we want it to do. For example, it acts on the tensor product of any P of n module times V. This is the specific defining representation. And it commutes with the action of P of n on that space. That's an extra calculation you have to do, but it commutes with the action of P of n just like you would want it to. And so it sits in the centralizer of the action of P of n on this space. P of n acts on V, these things act on V. All right, so let's take a look at an example. If I just take V tensor V. V is a P of n module, V is a GLNN module. Well, I pick my basis very specifically. This is the same basis as I picked to get that nice decomposition of P of n. And I look at this vector, which looks, it sits in the, not the symmetric part, the other part, sorry, noun problems. But it is a generator for a trivial module because of the super action. Anytime you pass by an odd part, you pay for it with a minus sign. Okay, so this spans the unique trivial module. And you can think about the centralizer of P of n on this space of V tensor V. And it's generated, it has three-dimensional algebra for big enough n. And it's generated by the identity, the super swap. Okay, so it's the flip, usual transposition. Pay for it by, oh, these should be just degrees. Sorry about that. And then you've got this take beta and beta dual. So it's going to map V tensor W to beta of V and W times this trivial generator. Those are the three generators for this centralizer algebra. Well, if you go ahead and think in diagram algebras like I do, you draw nice pictures like transpositions and cap cups. You get into a little bit of trouble if you do that because in this algebra you don't quite get the same relations as you would in, say, the Brouwer algebra. And so you step up and you say, okay, I'm going to mark my diagrams, and there's a nice marked Brouwer algebra. Moon constructed the sign Brouwer algebra, then Kujawa and Tharp moved it up to this marked Brouwer algebra, and the relations have to do with moving markings past each other and things like this. But this is the non-semi-simple case. If you square your beta beta star, you get 0. Why? Because if you compute beta on this, you will get 0. There's a lot of cancellation. Okay, so in particular, if you take our favorite omega and you act on this space, you get S plus E, which is the same thing as in the Brouwer algebra, looking at the UC's Murphy elements for this small little case up to a normalization. This is exactly what you get. The first UC's Murphy element is maybe a 1, S plus E or S minus E, depending on how you like to normalize your E's, but that's exactly what you would get. Okay, fantastic. So now let's think about translation functors. So I'm going to let this theta prime be a translation functor by tensoring by V. Take this omega, which is my favorite sort of fake split Casimir. It commutes with the action of P of V. So it gives a natural endo transformation of this translation functor. Similarly, you can sort of split them up over across, say let this act on the ith factor and the jth factor, and then that's going to also commute with the action of P of V, so I get a nice endomorphism of the endofunctor translate by D copies of V, fine. Now, if I sum these up, fix a J, and add up all of the omega ij's less than that, this is exactly what you would build if you were looking at UC's Murphy elements in the Brouwer algebra, or in the affine version of that, is these sum up over these, take these factors plus these factors plus these factors plus these factors and so on. And then that forms a commutative family of endomorphisms of this thing. And it forms a large enough family that you can start to get at some of the information. So these are exactly analogous to UC's Murphy elements in this algebra. Okay, but I want to get some information out of this. So let's take this translation functor composed with a projection onto some kth eigenspace of this omega. Well, that happens to be exact and is 0 for non-integer values. And so you can say, all right, this translation functor is exactly the sum of all of these translate and project, where I range over the integers. Nice discrete structure. Okay, so here's some combinatorics that we got out of this. I'm going to draw my weights as these weight diagrams that are sequences of dots that are either filled or not. So I'm going to take a dominant weight, and I'm going to let lambda bar be the row shift of that, where row is exactly the staircase partition. So I go from an integer sequence that's weakly decreasing to an integer sequence that's strictly decreasing. Okay, and I'm going to let C lambda be the parts, the length of the parts that appear, and these are all integers, and they're distinct now because I've done a row shift. All right, I'm going to draw a sequence of dots corresponding with the integers, where a filled dot means that the weight is in lambda bar, and an empty dot means that the weight isn't in lambda bar. Okay, so for example, if n is 4, I started with an integer sequence of length 4, weakly decreasing, so it's all zeros in this case, and then I row shifted it. So then I get 3, 2, 1, and 0, and that's exactly what these dots are. 3, 2, 1, and 0. Or if I look at row, a row shift of row is 6, 4, 2, 0. Take row plus row. So these weight diagrams, you have exactly one part of each length in gamma bar, and that's what C lambda is doing. So for example, lambda has distinct parts if and only if each filled dot has at least, or each two filled dots has at least one empty dot in between them. These are exactly the ones that have been proven that are where the CATS modules are equal to the simples. Under our dominance order, you have lambda is less than mu if the ith filled circle of lambda is to the right of the ith filled circle of mu. So for example, this is less than that. So to give you a feel for the sorts of results that we've got, let's apply the translation functors to some CATS modules. So if you take your thick CATS modules, which are a standard object here, apply the translation functor. What do we get? We get equality exactly when you look at, all you have to look at is the k, k minus 1, and k minus 2 parts of the weight diagram, and you get a picture like this. The shift of k lambda, so if lambda starts like this, where there's no lengths apart, parts of length k or k minus 1, but there is a part of length k minus 2. And the next one, there's no parts of length k minus 2. There is one of k minus 1. There isn't one of length k. I don't care what else is going on in the world. Then, when I shift and project, I get one of these. If, on the other hand, lambda starts out looking like this, and I shift and project, I get one of these. It shifts it back. So if it was here, it shifts it forward. If it's there, it shifts it back. So this is sort of like add a box or remove a box. If I've got two weights, right, what does this look like? This was, lambda wasn't a strict partition. It had two parts of equal length before I shifted. So then something funny happens. And at that moment, as long as I didn't have three of them, if I had a dot here, I would have had three parts of the same length. But if I just have these two, and I shift and, or sorry, here we go, sorry. No, I'm reading them wrong. There we go. So I had two parts of distinct length, but they were one apart. Then it sits inside of a short exact sequence where they're next to each other and they're next to each other, but it's add or remove a box. And otherwise, it's 0. So nice, I can move these thick CATS modules around in my category. Shift and project, and I know exactly how it works. Similar thing for thin modules, except for it's sort of the other way around. You want to start with things that have two adjacent parts, and you shift, and one of them moves over. One of them becomes longer. Two adjacent parts, one of them becomes shorter. Or if I didn't have two adjacent parts, then, or if I didn't have two adjacent parts, then it's add and remove a box, and it fits inside of a short exact sequence. Otherwise, 0. So these shift and project operators have really nice combinatorics, but the combinatorics is legitimately different. These two modules behave very differently. Sorry? Yeah, so you take K lambda, you tensor on V, and then you project onto the kth eigenspace of omega. Oh, sorry. This was the parity switching. Yeah. So swap the V0 with the V1 part. Yeah. Yeah, exactly. Sorry. Yeah, this is the same thing. So parity switch, parity switch. Yeah. Yeah. Okay. So why have I been using primes? It's because we're trying to head towards some kind of diagram algebra. If I take the theta k to be the translate and project, but maybe I apply a parity switch or not, depending on what k is, and I let theta be the sum of that, well, these are still exact functors, left and right adjoint to +1 or -1, and most wonderfully, if you look at, say, you move to the growth and deep group, or you look at up to some natural isomorphism, which we construct, these satisfy relations that if you've lived in the diagram algebra world, look awfully familiar. So, up to natural isomorphisms, you have the kth one squared is 0, they commute if they're far apart, and otherwise they satisfy sort of smash relations. K plus 1k is k, or k minus 1k is k. This is exactly the sorts of relations, forgetting this, these relations are the sort of things that you see in the Temperley-Lieb algebra. You also see them in the Brouwer algebra. The Brouwer algebra has twists, the Temperley-Lieb algebra doesn't. The Temperley-Lieb algebra is the Brouwer algebra, but with no crossings. And this is exactly setting the parameter in the Temperley-Lieb algebra to be 0, which is the non-semi-simple case. So this is exactly the infinite Temperley-Lieb algebra with parameter 0, and that's what these functors generate up to isomorphism. Both the theta and the theta prime at the level of the growth and deep group satisfy these relations. There's a little bit more of a natural isomorphism if you go ahead and do the work of doing the parity switch. To our knowledge, this is the first time that we've seen the non-semi-simple Temperley-Lieb algebra acting category. If you have other examples, we'd love to hear them. All right. So a few other results that we have, if you're interested in knowing more about the paraplectic Lie algebra, we've done decompositions and filtrations of projections in terms of cat modules and cats modules in terms of simples. We've done translation functors applied to projectives and simples. Multiplicity-free results, for example, if you compute Hom between projectives, the multiplicity is 0 or 1. Or if you do take a simple, shift and project, that's a multiplicity-free decomposition. So if you like to draw Bernoulli diagrams, you get to draw a lot of Bernoulli diagrams here in nice ways. Sockles and cosockles of cats modules, and blocks of the category. Computed nicely with you take these weight diagrams, and there's nice combinatorial results with these arrow diagrams where you attach these dots with those dots according to arrows, and then you shift the dots around and things like that to compute lots of these sorts of things. But I would be remiss as a combinatorial representation theorist myself. That's my bread and butter, is Schur-Weil duality. I do diagram algebras. To not tell you a little bit about the sorts of things that we're heading towards. So the next paper that we're working on now is all about the cyclotomic marked Brouwer algebra. So I said a little bit about, I had this centralizer algebra and these operators in the centralizer algebra where I said, oh, they look like Brouwer diagrams, except you have to mess with it a little bit. The cyclotomic version of this is exactly what we'll get out of using these omega operators. So let me take talk a little bit about that. I go until, what time? 4:20? 4:20, fantastic, beautiful. Okay, so here we go. What is the marked Brauer algebra? I live and breathe diagram algebras, so I couldn't help myself. The Moon in 2003 was trying to get at the representation theory of this paraplectically superalgebra and constructed what was called the signed Brauer algebra. And then Kujawa and Tharp came along and took that and melded it in with the Brauer algebra into something called a little bit more universal object called the marked Brauer algebra. So here's the marked Brauer algebra. What do? You take Brauer diagrams, which Brauer diagrams is you have D dots up top, D dots down below, and you connect the diagrams either with through strands or with horizontal strands as long as everything is a bijection. And then you mark the non-through strands. Every cap gets a diamond, every cup gets an arrow, but the arrows can go back or forth. And then, how can you tell if two diagrams are the same? Well, it's equivalence up to moving diagrams around, except for little local relations that have to do with these markings. That if I flip an arrow, I pay for it with an epsilon, whatever epsilon is, it's plus or minus 1. And if I have a little coil with an arrow on it, well, that flips an arrow, and so I pay for it with an epsilon. Okay? And then, it doesn't matter if you're talking diamonds or arrows, if I vertically move one dot past the other, even if they're in like really different places in the diagram, I pay for it with an epsilon. Okay, so multiplication is given by vertical concatenation, which means if I have two diagrams, I stack one on top of the other, I glue the dots in between, and I might get some of these relations, but I also might get closed loops. If the closed loop has at most I need the closed loop to be empty, and then I replace it with a delta, that's that other parameter, whatever that is. And how do I get rid of all the caps and cups have markings on them? I get rid of them by these relations. That if I have an arrow pointing towards a diamond, I get this, and if I have an arrow pointing away from the diamond, I pay for it with an epsilon. I should always have an arrow and a diamond on the loop. This relation?
Yeah. You have a sign.
The arrow is on one side of the...
one side, the other.
And it's the other.
You cannot move over.
That's right. I mean, you can with a sequence. So you would, if you want to move it past, what do? You say, this is that. So you'd pay for it with an epsilon. If you want to move an arrow past a diamond, you pay for it with an epsilon. Yeah. Yeah, the arrows and diamonds slide past crossings. They're different from your beads. But you always have an arrow on a cup, and you always have a diamond on a cap. And so if you want to think about sliding past a crossing, you're moving the crossing past a cap or a cup. Let's do a little bit of a calculation. Here are my relations. Let's say we take this diagram and we multiply by that diagram. Okay? Well, what are the things that I have? Well, one way that I could resolve this is, first I want to get rid of this loop, or this, not a loop, but a little kink. Well, I can unkink it with an epsilon. So that was this. And now, if I want to move, I can reduce, this thing has too many decorations on it. It should just have one diamond. So if I want to resolve this, I can use this relation. So I pay for it with an epsilon, but epsilon is plus or minus 1, so I get back to no coefficient. Of course, I could have done the same thing here. You don't have a sign, but you can't move it yet because these two are not adjacent yet in your vertical concatenation. So first you have to move the diamond past the diamond, pay for it with a sign, then you get to resolve this, You pay for it with another sign. Okay, so it's well defined. So in order to do these kinds of things, I really need them to be next to each other in some kind of vertical sense. So it drives you crazy if you really want to be able to draw like straight lines, because you can't. You have to keep your ups and downs precise because you have things like this. Okay. So that's our marked Brouwer algebra. Well, it's basically just the two things that we had before. It's basically just the Brouwer algebra or the sign Brouwer algebra. By what do we choose? If epsilon is 1, this is the Brouwer algebra. All of these funny relations that I had with when do you get to move marks past each other, they're trivial if epsilon is 1. When do they come into place? They come into place when epsilon is -1. Well, when epsilon is -1, it turns out the multiplication is not well defined on the loops. Right? Because you get, when do I have the arrow pointing towards the diamond and when do I have it pointing away if they're on a circle? That's not a well-defined multiplication unless the circle is 0. So this is exactly, if epsilon is 1, you get the Brouwer algebra. If epsilon is -1, then delta better be 0, and that was the sign Brouwer algebra of moon. Well, one reason that you like to put these things together is that you're going to say, okay, I'm going to take representations of a thing, and I'm going to study the centralizer algebra, and it's that thing. So here we go. So if I say the marked Brouwer algebra is generated by your transpositions and your cap cups, back in our general setting of you started with GLNM, you put a form on it, a non-degenerate, homogeneous, supersymmetric bilinear form. That thing is either going to be even or odd. If it's even, I got the orthosymplectic Lie superalgebra. The orthosymplectic Lie superalgebra is the orthogonal and the symplectic wrapped up in one. Well, both for the orthogonal Lie algebra and the symplectic Lie algebra, if I study V tensor K on that space, and I act by, say, the orthogonal Lie algebra, and I look at its centralizer, I get the Brouwer algebra. Same thing for the symplectic. You have to worry about signs a little bit, but it's okay. It's still the Brouwer algebra. You just act a little bit differently. Okay, so the centralizer of the orthosymplectic Lie algebra should be something like the Brouwer algebra. The other case was when the form was odd. That's the paraplectic dude. Okay, so here's my beta. If I let beta star be the dual, if I let the S be this super swap, then the mapping cap cup to exactly what you expect it to be, beta beta dual, and SI to be the super swap on the right factors, then this gives a surjection. Maybe you have to add a little bit of an action of a center, it's okay, onto the centralizer algebra of this k-fold tensor product of the defining representation. What is the parameter? The parameters are the super dimension, which is the dimension of the even minus the dimension of the odd, and epsilon is -1 to the sign of beta. If it's even, this is 1. If it's odd, this is -1. If we had an odd form, we required that the dimension of V0 and V1 were equal. That gives us the 0 parameter, which is exactly the case when the sign Brouwer algebra was well defined for epsilon being -1. Otherwise, you can get non-zero parameters. So, back to our omega. How do we do something with this? So I'm going to let Sij be the transposition on the I and j strands, and Eij be the cap cup on the ij strands. This is the same thing as taking those super swap or the cap cup operators, but only applying them to those factors. So you can swap, apply, swap back. Well, then classically, in the Brouwer algebra, the Euclides-Murphy elements look like this. This is some constant, usually taken to be 1, doesn't matter, plus the sums over the differences here. This is exactly what you would get if you looked in the Sadov, which is where he studied the Euclides-Murphy elements of the Brouwer algebra. You can fiddle with this sign up to certain normalizations. Like Our omega was S plus E, not S minus E, but it's okay. Fiddle with it, you can get a normalization that you like. Then you define the degenerate affine version of the Brouwer algebra as you take the Brouwer algebra, and then you take a polynomial ring, and you define relations between the polynomial ring and the finite Brouwer algebra by whatever were the relations that this satisfied with the S's and the E's. You forget about the relations with each other, and you just look at the relations between passing past E's or S's, and that's the relation you get in the affine version. The degenerate affine Brouwer algebra, the degenerate affine BMW algebra, the degenerate affine Wenzel algebra, or the VW algebra, these all are different names for the same thing, comes from taking these Euclides-Murphy elements, ripping them out of the algebra, and adjoining them back on. Okay? The reason that we like this is these all pairwise commute. So if you're trying to study the representation theory of this Brouwer algebra, you can look at, take the sub-algebra generated by the Euclides-Murphy elements. They pairwise commute, so that thing is abelian. So its simple representations are one-dimensional. So they're just a list of eigenvalues. Then you induce up, and those things decompose, but they decompose in a very nice controlled way. And so you can study all of the representations by central characters based on linear combinations of these Euclides-Murphy elements. In this affine dude, the center is actually really legitimately symmetric functions in this polynomial ring with a condition. Okay, so it's really central characters that you use to study this. So we'd like to do the same thing for the Mark-Brouwer algebra. The Mark-Brouwer algebra is going to tell us things about V tensor D of the paraplectic Lie superalgebra. And if you're trying to do translation functors, what do? You tensor on you tensor on V, and then you project. And then you tensor on V, and you project, and you tensor on V, and you project. And so really what I want to look at is M for some special module, tensor a bunch of V's. Well, the Mark-Brouwer algebra isn't very good at that, but the affine version will be. These Y's are going to act on the M part, and then the Mark-Brouwer stuff is just going to act on the V to the D stuff. So in the classical case, the Yi's act on M tensor V to the D by the split Casimir. You take the classical split Casimir, V tensor V star, add up, then you apply that to the M factor in the jth V, the first V in the jth V, the second V in the jth V, and so on. You add that up. That forms a nice representation, nice action of the Euclides-Murphy elements. Look at the eigenvalues of those things. In particular, the first one picks up contents of outable boxes of whatever this thing is parameterized by. Well, now we have an analogous tool to build an action of the Euclides-Murphy elements in the Mark-Brouwer algebra. That's this omega. So do the same exact thing where you add these things up, which we said already was a nice big commutative family of operators. So the goal is to define this degenerate affine Mark-Brouwer algebra and the cyclotomic quotients and classify the representation theory. So that's what we're working on now. All right. I should make a plug very quickly, sorry. This project came out of the Banff Women in Non-Commutative Algebra and Representation Theory project. And just to let you know, many, many beautiful papers are coming out of this. You'll see Ellen was here. Our group was 2 groups slammed together, so you saw there's 10 authors on this paper. But it was a wonderful, productive time, and keep an eye out for papers out of that session. Okay.